Going back to the fault models, right? So we have looked at single stacket faults, transition delay faults, bridge faults, then this IDDQ testing, right? There are also other fault models for digital logic. Okay, one of them is called cell aware faults, cell aware testing. See, in a cell aware test, see, if you give me an AND gate or an XOR gate, okay, or something like that, when we do ATPG, if you give me this XOR gate, let us say I call it A, B and C, ATPG will look at A stuck at 0, A stuck at 1, B stuck at 0, B stuck at 1, C stuck at 0, C stuck at 1. These are the only faults it will consider. But inside this gate, there is some structure. We don't know how this, this XOR gate is actually built. Okay. Suppose somebody had built the XOR gate like this. See, this is an XOR gate, which is based only on NAND gates. Just because I drew a big black box here, is it okay to just look at A0, A1, B0, B1, C0, C1? There are many internal nodes, maybe D, E, F. Right. So, maybe these are stuck at 0, stuck at 1. So, these are also important. So, by ignoring these internal faults, cell internal faults, must be considered. That is what they are arguing. See, if you look at the XOR gate alone, we can say there can be a stuck at 0, stuck at 1, stuck at 0, stuck at 1, stuck at 0, stuck at 1. In an XOR gate, it may not be easy to eliminate based on equivalence. See, a stuck at 0 and stuck at 0 here, they may not be equivalent. See, if I make a stuck at 0 here, the functionality will be, let us say this is A, B, C. A stuck at 0 means C will become B, right? A XOR B, when A is 0, is nothing but C equal to B. When B is stuck at 0, C will be A. When A is stuck at 1, C will be B bar. When B is stuck at 1, C will be A bar. When C is stuck at 0, the output is 0. When C is stuck at 1, the output is 1. So, you can see everything is different. Okay. So, there is no equivalence as such. What about dominance? Okay. Let us look at A stuck at 0. What is a good test vector for A stuck at 0? We have to apply 1 here to activate the fault. And frankly speaking, B can be either 0 or 1. So, both 1 0 and 1 1 will work. right? We will have to apply a 1 to activate the stuck at 0 fault, but the other can be either 0 or 1. Both of them will propagate the fault. Similarly, B0, A can be either 0 or 1, but B has to be 1. C stuck, let us say A stuck at 1. We have to apply 0 and the B can be either. Similarly, B1, B has to be 0, but A can be either 0 or 1. Finally, C0. In order to apply activate the fault C stuck at 0, we can either apply 0 1 or 1 0, and C stuck at 1, we have to apply 1 1 or 0 0. So notice that there is no dominance also. So we have to consider all the faults. But if you are willing to go inside on the construction of the XOR gate, the fault list is much bigger. There is A0, A1, B0, B1, then D1 0, D1 1, right? Then D2 0, D2 1. So this is D1 and this is D2. Similarly, A1 0, A1 1, A2 0, A2 1. So according to our checkpoint theorem, these are the fault lists. So there are a lot more faults. Here we only looked at 6 faults, but here we are looking at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 faults. We may be able to eliminate a few more by equivalence and equivalence, but it may not be too many that we can eliminate. So what is the advantage of considering the internal faults like this? The advantage would be that it helps me to isolate what could be wrong. If I draw the box very big, okay, imagine I have a decoder, 2 to 4 decoder. If I say, look, there are A, B, let us say D0, D1, D2, D3, and if I am willing to only look at the inputs and outputs and consider stuck at faults on those, then we are possibly forgetting that there may be a lot of faults inside. What about an ALU? It has maybe it's a 8-bit ALU. There is a carry input, carry output. Then maybe there are some things like overflow. Then what is it? Carry, output, overflow, underflow. These outputs are also maybe there. There may be some difference, etc., some result, and this may represent the operation. It may be add, subtract, logical AND, etc., etc. Okay. If I now only look at the stuck at 0, stuck at 1 on the periphery, right, then I may have left out so many faults which are inside. So that is what cell aware testing says, right? There may be something internal to the cell that we are ignoring if we only look at the faults at the periphery. So, where is it useful? So, cell aware faults means consider faults internal, also internal to the cell. These may be the same old single structured faults, that is okay, but do not ignore them, because as I just pointed out, if you only look at the periphery of the XOR gate, you only have 6 faults, but when you open it up, you see lot more. If you are willing to open it to the transistor level, you may even see more faults. Okay, so if you look at transistor level circuit, you may see even more faults. It will complicate your testing, no doubt. Okay, you have a much bigger list of faults to deal with, but it is important when we are doing things like industrial electronics. Or when you are doing automotive. So, if you only look at you know, cell external faults, okay, if you only do faults like this, then maybe you are missing out some faults which are internal. So, that is the basic idea of cell aware testing, and you should remember that it is used in automotive testing, testing of automotive electronics and industrial electronics. Okay.